to General Science. Today we are talking about a new unit. We're separating this, and we're going to talk about in this unit atomic weights. We're going to talk about this cool number called Avogadro's number. It's just named after a dude named Avogadro. And then we're also going to talk about the mole. The mole and Avogadro's number are super interrelated. Okay, so if we take a little review of what we've learned in the past. So if we're looking at the periodic table and I take a look at chlorine and I kind of expand what that looks like in a box, I'm going to see Cl, which is the symbol standing for chlorine. I'm going to see that atomic number at the top, 17, and then I'm going to see this other number at the bottom. That's going to be the atomic weight. Okay, we'll talk about that in a second. Let's first take chlorine, and let's say that there was 17 and then 35. If you recall, these numbers tell me a lot about the atom that we're looking at. So the atomic number, first of all, can be told, and then the mass number, the protons, electrons, and neutrons. Okay, so atomic number. So for the atomic number, we can just look at the periodic table, also at that 17 on the bottom. The mass number is going to be that top number that we see, 35. Now, protons are related to the number, the atomic number, and so are electrons. So those are both 17. Now, the number of neutrons is the mass number minus the atomic number, so that'll be 18. Okay, so that's just a quick review on how to do that. So now we're going to compare two different chlorines. So one is 3717 chlorine and one is 3517. Now notice that they're both 17. That's because this is the atomic number, and for chlorine, the atomic number is unchangeable. If it had a different atomic number, it would just be a different atom, okay, or a different element. So we're just going to be talking about chlorine here. Now we see that 37 and 35 are different, right? So 37 has a greater mass number, okay, which means it has a greater number of neutrons. And since it has more stuff in it, it must have a greater mass. Okay, so we're starting to get sort of an idea of something about masses. Okay, so these are called isotopes. So isotopes are two atoms of the same element, but they have different atomic weights, okay? They have different masses, and that'll be due to different numbers of neutrons, okay? So they might have more or less neutrons, making them isotopes of the same element, and different isotopes will actually behave differently. Okay, so let's say we take another example. Let's say we have sodium, okay, in here, and we're kind of expanding its view in the periodic table, and we see this number down here, which is the atomic weight. Okay, so the atomic weight of sodium is 22.9898. Okay, now this number is based on the carbon-12 scale. So you can't quite see it there, but it's carbon-12 scale. So one atom of carbon-12 is equal in weight. It weighs 12 atomic mass units, which we will abbreviate as AMU. Okay, so it's kind of just like any other thing, like a pound or a gram, right? It's just a way of measuring something. So 1 AMU is equal to 1/12 the weight of a C12 atom, okay? So that's kind of important to note there. So that means that if we take sodium and we figure out, well, what's its atomic weight? Well, one atom of Na is going to be weighing 22.9898 AMUs, okay? Moving on to the next thing. So let's say we take an atom of boron. Okay, so I'm going to draw out what it looks like on the periodic table, and I'm just going to draw this bottom number, right? That's the atomic weight. Okay, so I know that one atom of boron weighs 10.81 AMUs, right? That number just gives me the atomic weight of one atom. Okay, so it's 10.81 AMUs. Okay, so now this is going to lead us to a discussion on Avogadro's number. Okay, so if we take a look at 6.023 times 10 to the 23rd atoms of boron, so if we were to take that many atoms of boron, that would weigh 10.81 grams. Okay, so that number, 6.023 times 10 to the 23rd, you should memorize. This is called Avogadro's number. Now, it's a super huge number of things, okay? Let's go ahead and consider the example of 1 dozen. Okay, so 1 dozen just means 12 of something, right? We've experienced that in our daily lives. A dozen eggs is 12 eggs. So if we have a dozen cars, that means we have 12 cars. Okay, now let's say I have 1 mole. Well, what is mole? We've never learned that before. Well, 1 mole is just equal to 6.023 times 10 to the 23rd of something. That's Avogadro's number again. Okay, so if I say I have 1 mole of cars, that means I have 6.023 times 10 to the 23 cars. Okay, that's the equivalent of, I'm going to write this huge number here. I have a lot of zeros. It's a huge number. It's going to be 602 sextillion 300 quintillion cars. Okay, that is a lot of cars. So it's a huge number of something, but remember that atoms usually is what we're referring to when we're talking about Avogadro's number, and atoms are really, really tiny. So to have a lot of them still doesn't mean like you have very much stuff. Okay, so 1 mole, consider 1 mole of phosphorus. Okay, so we're going to take a look at the periodic table, and remember that 1 mole is 6.03 times 10 to the 23rd. So we're looking at 6.023 times 10 to the 23rd atoms of phosphorus. So we want to know the weight of this. So we look at phosphorus and we expand that here. So phosphorus has this number on the bottom, 30.979. Okay, so that means that 1 mole of phosphorus is going to weigh 30.974 grams. Okay, so this number, Avogadro numbers, we're going to talk about in the future. It's just helpful to note that that number of AMU is equal to 1 gram. So 6.023 times 10 to the 23rd AMUs equals 1 gram. I will see you guys next time. Good luck on your homework.